So very good morning to you all. I welcome you all for today's EMF and transmission line session. Uh, I have shared a live YouTube link. You can watch in YouTube also. And before going to YouTube, you give attendance to your CR. So in my last class, I have discussed one very important topic, that is input impedance of a transmission line. Right. So as you can see here, the transmission line equations we have considered. These are the transmission line equations we have considered, and using transmission line equations and doing some mathematical simplifications, we have calculated or derived the expression for input impedance of a transmission line, right? So the procedure, in my last class I have explained in detail about the input impedance of a transmission line, right? So this is the input impedance of a transmission line which we have derived in the last class, right? Here you can hear gamma is propagation constant, right? Gamma is propagation constant, and where gamma is equal to alpha plus j beta, and alpha is attenuation constant, and whereas beta is phase constant, right? Alpha is attenuation constant and beta is phase constant, right? Now let us consider a lossless transmission. Lossless transmission line, right? Let us consider a lossless transmission line. So few classes back I have discussed about the lossless transmission line, and for a lossless what is meant by lossless transmission line? Just for recollecting, lossless transmission line in the sense where R is equal to G is equal to 0, right? So that is a lossless transmission line. So when R is equal to G is equal to 0, what we got for the lossless transmission line? Alpha is equal to 0 and beta not equal to 0, right? If you can remember this, alpha is equal to 0 and beta not equal to 0 for a lossless transmission line. So therefore, input impedance is equal to Z0 ZL plus Z0 tan H J beta L divided by Z0 plus ZL tan H J beta L. So class is not recording. Let me check. Right. Thank you. Right. So once again, let me repeat it. we have derived the input impedance of a transmission line, right? Let us consider lossless transmission line. Lossless transmission line in the sense attenuation constant alpha is 0, right? Attenuation constant alpha is 0 for a lossless transmission line, right? So therefore, keeping this in mind, let us try to determine the input impedance of a lossless transmission line. Therefore, input impedance expression we know Zn is equal to Z0, ZL plus Z0 tan H J beta alpha, right? Because gamma is equal to alpha plus J beta and alpha is 0, right? Alpha is 0. So therefore, gamma is equal to J beta. So therefore, simply substituting gamma, right? Simply substituting gamma is equal to J beta, you will get this expression. So this can be further simplified like this. Zn is equal to Z0 ZL plus J Z0 tan beta L divided by Z0 plus J ZL tan beta L. Since tan H J beta L is equal to J tan beta L, right? Tan H J beta L is equal to J tan beta L, right? So therefore, the input impedance will become like this, and this is the expression for input impedance of a lossless transmission, right? So this is the input impedance of a lossless transmission line. Zn is equal to Z0 ZL plus J Z0 tan beta L by Z0 plus J ZL tan beta L, right? So this is the input impedance of a lossless transmission line, right? So is it clear till now? So in this we have discussed the input impedance of a transmission line, right? And we can consider this equation as the input impedance of a distortionless transmission line, right? So this can be considered as input impedance of a distortionless transmission line. Why? Because in a distortionless transmission line, we know that alpha not equal to 0, beta not equal to 0, right? In a distortionless transmission line, we know alpha not equal to 0 and beta not equal to 0. But whereas in lossless transmission line, alpha is equal to 0, right? That we know. Alpha is equal to 0 and beta not equal to 0. Substituting these conditions, you will get this expression as input impedance, right? So I hope it is clear to you, right? Now let me switch on to another new topic. Okay, before that, before moving on to another new topic, let me do a small related problem here. Here you can see a problem. Just right. So here, so this is the problem which was given. So problem says that a certain transmission line operating at omega is equal to 10 power 6 radians per second, alpha is equal to 0.921 nepers per meter, and beta is equal to 1 radians per meter, and Z naught is equal to 60 plus J 40 ohms, and load impedance ZL is equal to 20 plus J 50 ohm, right? And we need to determine the input impedance, right? We need to determine the input impedance, right? So the given data, this is the given data, this is the given data, right? And from given data, it is clear that alpha not equal to 0 and beta not equal to 0, right? From the given data, it is clear that alpha not equal to 0 and beta not equal to 0. So therefore, we have to consider, right? We have to consider this problem, this relation. Zn is equal to ZL, Z naught, ZL plus Z naught tan H gamma L divided by Z naught plus ZL tan H gamma L, right? So this formula we need to consider to determine the input impedance, right? So from this it is clear that Z naught value is given, right? So this is given, Z naught is given, and ZL is given. You can substitute there directly, right? And what else we have? Let me determine tan H gamma L separately, right? Tan H gamma L, this is equal to tan H alpha plus J beta L. And what is L? L is also given, and in the given data, L is equal to 2 meter long, right? So here it was given, I have forgotten to write 2 meter long, right? Transmission line is 2 meter long, right? So therefore, this is equal to, what will get, is equal to tan H alpha L plus J beta L, right? Tan H alpha L plus J beta L, and this is in the form of tan H x plus Jy, right? So this is in the form of tan H x plus Jy, right? So if you want to do the problem, you need to know what is the expansion tan H gamma L, right? So without knowing what is tan H gamma L, you cannot complete the problem, right? So therefore, I will give you the expression what is tan H gamma L, then you can do it, right? So tan H x plus Jy is equal to sin H 2x divided by cos H 2x plus cos 2y plus j sin 2y divided by cos H 2x plus cos 2y, right? So this is the expansion of tan H x plus jy, right? So where here x is equal to alpha L and y is equal to beta L, right? X equal to alpha L and y is equal to beta L, and you know what is alpha L? L is 2, alpha is 0.2921, and beta is 1, right? Beta is 1. So substituting those values, first you determine this one, right? First you determine tan h x plus jy, and then substitute tan h jy here, right? Tan h jy in this expression, you will get and simplifying, you will get the final answer, right? So this is how you can we can do the problem, right? So if you do so, right, you will get, after simplifying the input impedance 60.25 plus j 38.79 ohm. This is the answer you're supposed to get, this answer, right? So you do it later, you do it, right? So don't simply skip, you do this problem later, right? So let me explain once again. Write down what is the given data first, whatever the problem is given, and the first and foremost step is write down the given data and what to determine. So we have written the given data and what to determine input impedance, right? So input impedance, we have two formulas, right? One is distortionless transmission line and another one is a lossless transmission. Which formula to consider? It depends on alpha and beta values. And here alpha not equal to 0, beta not equal to 0. So therefore we will consider this expression to determine input impedance, right? And substituting all the values and simplifying, you will get the answer. That's it, right? So that is about the problem, right? Next topic, let us move on to next topic, reflection coefficient, right? Another very important topic we are going to discuss now, right? So reflection of a transmission line, right? Reflection of a transmission line, right? So let me explain clearly here. Let me once again consider the transmission line. So this is the basic or conventional transmission line of length L. The transmission line may be of finite or infinite, whatever it may be, reflection coefficient is same. So Vs and E is terminated by a load impedance, right? E is terminated by a load impedance, and this is IL, load current, and load voltage VL, right? Along z axis, let us say. So along z axis means source is at z is equal to 0 and load is at z is equal to L, right? So this is the conventional transmission line, right? So which we have considered, right? So now when power is applied, let me define what is reflection coefficient. When power is applied at the input, to a transmission line, to a transmission line of infinite or finite, right? Infinite or finite transmission line terminated by its characteristic impedance. Z0 is characteristic impedance, right? when power is applied at the input to a transmission line of finite or infinite, right? Whatever the transmission line may be, right? And terminated by its characteristic impedance. So terminated by its characteristic impedance in the sense what? ZL is equal to Z0, right? Terminated by its characteristic impedance in the sense load is equal to load impedance is equal to its characteristic impedance, right? Then all the power, right? All the power is absorbed by the load, right? All the power is absorbed by the load, right? So that means what? All the power is absorbed by the load in the sense what? The transmission line is perfectly matched, right? You know, maximum power transmission theorem, right? Maximum power transfer theorem. So what is maximum power transfer theorem? Maximum power transfer theorem says that whenever load impedance is equal to source impedance, then maximum power will be delivered to the load. Once again, whenever then maximum power will be delivered to the load. That is called as maximum power transfer theorem, right? So therefore, here whenever load impedance is equal to the characteristic impedance of a transmission line, right? Right? So that means ZL is equal to Z0 and which is equal to ZS, right? Whenever load impedance is equal to its characteristic impedance, right? Then the maximum power will be absorbed by the load. Just a minute. Right? On the other hand, if the transmission line, if the transmission line is terminated by an impedance, by an impedance other than its characteristic impedance, right? Its characteristic impedance, then part of the wave or part of the power, is absorbed and rest of the power will be reflected back, right? So here I'm giving you two conditions, right? So one is when transmission line is terminated by its characteristic impedance, and second condition when transmission line is terminated by an impedance other than its characteristic impedance. These are the two conditions here. So in one condition, if the transmission line is terminated by its characteristic impedance, maximum power will be absorbed by the load, and whereas in the second condition, if the transmission line is terminated by other than its characteristic impedance, then only part of the power will be absorbed, and maximum power will be reflected, right? Maximum power will be reflected, right? Why maximum power will be reflected? Because of the impedance mismatching, right? Because of the impedance mismatching, maximum power will be reflected back, right? So therefore, reflection coefficient, right? Reflection coefficient is defined as the ratio of, right, is defined as the ratio of reflected wave or power to the incident wave or power, right? So this is reflection coefficient, right? Reflection coefficient is the ratio between a reflected wave to the incident wave, right? So reflection coefficient which is represented by this symbol capital gamma, right, is equal to ratio between reflected wave or reflected power or reflected voltage, right? If we consider in terms of voltage, then it is reflected voltage to the incident voltage, right? Incident wave, right? Reflected wave to the incident wave, right? So therefore, capital gamma is equal to VR by VI, right? VR by VI, right? And let us say this is equation 1, right? And one more thing, from transmission line equations, from transmission line equations, we know that V is equal to V naught plus e power minus gamma z plus V naught minus e power gamma z, right? So this is the transmission line equation related to voltage, right? So earlier I have given you that the first term, right? So in this, the first term is represents the forward voltage term, right? First term is the forward voltage term, and second term is the reverse voltage, right? First term is the forward voltage and second term is the reverse voltage. In other words, forward voltage or incident voltage, incident voltage, and this is uh, reflected voltage, right? Forward voltage or incident voltage, and second term is reverse voltage or reflected voltage, right? So therefore, the reflection coefficient, capital gamma is equal to reflected voltage V naught minus e power gamma divided by V naught plus e power minus gamma, right? V naught minus e power gamma divided by V naught plus e power minus gamma, and let us say this is equation 2, right? Is it clear? So from the transmission line equation, right, from the voltage equation, we know that the first term is forward voltage and the second term is reverse voltage, right? Second term is reverse voltage, right? So therefore, reverse voltage term divided by forward voltage term is nothing but a reflection coefficient, right? So this is the definition of reflection coefficient. Now let us determine a solid mathematical equation for reflection quotient, right? So to determine the reflection quotient, right? So here you can see there are two terms here, right? V naught minus, right? So in equation 2 we have V naught minus, and in the denominator we have V naught plus, right? So therefore determine V naught minus, right? Determine V naught minus and V naught plus, right? Determine V naught minus and V naught plus, and substitute in the above equation. We will get the final expression for deflection quotient, right? Now how to determine V naught minus and V naught plus, again considering transmission line equations, right? So you can observe whatever the topic I'm discussing, I'm using the transmission line equations, right? In all the topics I'm using transmission line equations, right? So therefore transmission line equations is very important. So we know that V is equal to V naught plus e power minus gamma z plus V naught minus e power gamma z, and I is equal to 1 by z naught V naught plus e power minus gamma z minus V naught minus e power gamma z. And let us say this is equation 3, right? So this equation can be simplified like this: I z naught is equal to V naught plus e power minus gamma z minus V naught minus e power gamma z. And let us say this is equation 4, right? So therefore solving equations 3 and 4, we can determine V naught minus and V naught plus, right? How? By adding, right? Adding equation 3 and equation 4, right? Adding equation 3 and equation 4, what will get? V plus I z naught is equal to, right? V plus I z naught. Okay, let me write down once again so that it will be more clear to you, right? So V is equal to V naught plus e power minus gamma z plus V naught minus e power gamma z, and equation 4, I z naught is equal to V naught plus e power minus gamma z minus V naught minus e power gamma z, right? Adding these two, right? Adding these two, what will get? V plus I z naught is equal to, adding these two, what will get? So the second terms will get cancelled here, right? So this one and this one, right, will get cancelled, and we will get 2 V naught plus e power minus gamma z. So therefore V naught plus is equal to, right? V naught plus is equal to what will get? 1 by 2 V plus I z naught e power gamma z, right? And let us say this is equation 5, right? This is equation 5, right? So similarly, we have added equations 3 and 4, right? Adding equations 3 and 4, we got V naught plus, and now let us subtract, subtracting equations 3 and equation 4, right? So V is equal to V naught plus e power minus gamma z plus V naught minus e power gamma z, and I z naught is equal to V naught plus e power minus gamma z minus V naught minus e power gamma z, right? Subtracting. So subtracting here, subtracting subtracting what will get? V minus I z naught is equal to, now here what will get? This term and this term will get cancelled, right? Because we are subtracting, right? Therefore and here 2 V naught minus e power gamma z, right? So therefore V naught minus is equal to 1 by 2 V minus I z naught e power minus gamma z, right? So this is equation 6, right? So therefore from equation 5 we have V naught plus, and from equation 6 we have V naught minus. So therefore substituting in equation 2, right? Substituting in equation 2, right? So therefore from equations, right? Substituting equations 5 and 6 in equation 2, we have gamma is equal to 1 by 2 V minus I z naught e power minus gamma z e power gamma z divided by half V plus I z naught e power gamma z e power minus gamma z. This you will get, right? After substituting equation 5 and 6 in equation 2, we will get this one, right? So simplifying this, right? Simplifying this, reflection coefficient is equal to V minus I z naught divided by V plus I z naught, right? So this you will get, right? So because those terms will get cancelled, right? So half here, half and half, and these two terms. What is your question? Someone is asking one question. Let me pull it out. Negative term for what? Just wait. Let me pull it out. Your question. E power, for e power you will get negative. Yes, we will get negative because we are taking e power to the right hand side, to the other side, right? So because we are taking e power to the other side. So when we are taking e power to the other side, right? So let me clarify it. So this we are taking to the other side, right? So this we are taking to the other side. So therefore you will get minus here, right? You will get minus here. So similarly here also, here we are determining V naught plus. So therefore, taking this term to the other side, and here we'll get plus, right? Here we'll get plus. Is it clear? Right? So this you will get, right? And wait. Right? And here this term is 1, this term, right? So e power 0 you will get. So this is 1, and here also e power 0 you will get, and this is 1, right? So this is equal to 1, and this is equal to 1. So those two will get ones, right? So finally you will get this expression. And one more thing is reflection occurs at the load side, right? Reflection occurs at the load side, right? Because load is terminated, right? So when load is terminated with its characteristic impedance, no reflection. When load is terminated with an impedance other than its characteristic impedance, then reflection takes place, right? So therefore, reflection occurs at the load side, right? Reflection occurs at the load side, right? So therefore, at the load, V is equal to VL, I is equal to IL, right? At the load, V is equal to VL and I is equal to IL. So therefore, reflection coefficient will become VL minus IL Z naught divided by VL plus IL Z naught, right? And here, if you taking IL common on both the numerator and denominator, right? Taking IL common, we have VL by IL minus Z naught divided by VL by IL plus Z naught, right? And this is equal to ZL minus Z naught divided by ZL plus Z naught. Since ZL is equal to VL by IL, right? So this is the reflection coefficient, right? Expression, final expression for reflection coefficient, right? So therefore, reflection coefficient ZL minus Z naught by ZL plus Z naught, right? And let me verify, right? Let me verify this, right? So let me verify this, right? From the definition, when load impedance, right? When load impedance is equal to its characteristic impedance, when load impedance is equal to its characteristic impedance, no reflections, right? No reflection. When load impedance is not equal to Z naught, then reflection exists, right? So that is what from the definition, right? So therefore, when ZL is equal to Z naught, what is reflection coefficient here? When ZL is equal to Z naught, reflection coefficient, right? From the formula, right? From the formula, reflection coefficient is equal to 0, right? Reflection coefficient is equal to 0, right? So because substitute here, ZL is equal to Z naught, right? So when ZL is equal to Z naught, then the numerator term will be 0. So therefore, 0 by something is 0. So therefore, reflection coefficient is 0, right? So therefore, whenever load impedance is equal to characteristic impedance, then reflection coefficient is equal to 0. Reflection coefficient is equal to 0 in the sense what? No reflections takes place. No reflections. That means reflection coefficient is 0, right? But whereas when ZL is not equal to Z naught, then reflection coefficient is not equal to 0, right? When ZL is not equal to Z naught, then reflection coefficient is not equal to 0, right? So this is what reflection of a transmission line, right? So in this class we have discussed two topics, right? Number one, input impedance of a lossless transmission line, right? Number one, input impedance of a lossless transmission line, and second one, reflection coefficient of a transmission line, right? So reflection coefficient is nothing but a ratio between reflected voltage to the instant voltage, right? Reflected voltage to the instant, because here we are speaking in terms of voltage, so therefore here wave or voltage, right? Wave or voltage, reflected wave or reflected voltage, instant wave or instant voltage, reflected voltage to the instant voltage, right? And finally we have derived the expression for reflection coefficient, which is ZL minus Z naught by ZL plus Z naught, right? So with this, let us close our session.